17 is about thermodynamics. We did thermochemistry in the first semester, which was just focused on heat absorbed in versus heat given off. Right? We called that enthalpy. Okay? Thermodynamics goes a little bit past that. We'll talk about what free energy is, but essentially we'll be answering the question, why do chemical changes happen? And what the difference is between a spontaneous process that happens on its own versus a non-spontaneous process, which can only occur if energy is constantly supplied. Okay? So, the difference there, and a balloon full of hydrogen, or what were you guys exploding last? Soda cans or something like that last semester. Yeah, soda bottles. What was that? If something like that explodes, we have to supply activation energy, okay, for that. That's why you need a flame. But then the reaction completes on its own. That's not a constant supply of energy. When we're talking constant supply of energy, that means sitting something on a hot plate or something like that, or feeding light or heat or something into the reaction constantly. And if you cut that off, the reaction stops. Okay. Yep, the melting of an ice cube. Well, and we'll talk about temperature, but you can sort of think of it that way.
So does that mean that it's not maybe activation energy?
Correct. Activation energy is just something that activation energy is a kinetic term because there will always be, there's a range of energies of the molecules. If we need this much energy for a reaction to happen, even if that's really high, there will still be 1% or so of molecules that have enough energy to do it. Okay? So a really high activation energy is a really slow reaction. Okay? If we supply activation energy, we can get a reaction to go fast, okay? But that's not a constant supply of energy. We could supply enough activation energy for it to get going, and the energy released from that supplies the activation energy for the rest of it. Okay? So a non-spontaneous process is one that is literally uphill in energy, okay? Where we have to supply all of the energy in to even form products at all. Okay? But we'll refine that definition a little bit better. If we have a chemical reaction A producing B that is spontaneous, as written, how would we be able to, here, if that is spontaneous, then that must mean that this reaction is what do you think? Anti-spontaneous? Okay. By definition, a reaction that's spontaneous in one direction will be non-spontaneous in the other direction. Okay? So, what would I think? Strong acid and strong base. Yeah. Yeah. Mm-hmm. Yeah, I think we can think of it like that. We'll get a little better example in a minute. If we think about potential energy is really pretty easy to think of in classical physics, right? If we're pulling up on that weight, we're building up the potential energy, which is released if we let go of it. Okay? So the higher we pull it up, the more potential energy it has, the more damage it'll do when it comes crashing down. Okay? So chemical potential energy is a little more difficult to envision, but chemical potential energy works the same that mechanical potential energy has. There's chemical potential energy built into something like this solid sodium chloride, so that when it is put in water, it will spontaneously dissolve. Okay? And the process of NaCl solid becoming Na and chloride aqueous is spontaneous. Okay? If you put, at least it's spontaneous before it's saturated. Okay? The reverse reaction is non-spontaneous. Okay? If you're not changing anything else, sodium chloride ions don't just group themselves together and form solid sodium chloride. Okay? At least in the absence of some source of extra potential energy. We'll talk about how that can happen. Okay? But if that's the spontaneous direction, the reverse of that is non-spontaneous. So to figure out what happens on its own spontaneously, that's determined by thermodynamics, the energetic relationship between reactants and products. So we're going to start to be thinking, what has more potential energy? Are the reactants higher in energy, or are the products higher in energy? Okay? That's the kind of thing that determines the direction of reaction. And just like potential energy, something with high potential energy will spontaneously change to something with low potential energy by something dropping. Okay? A chemical substance with high potential energy will spontaneously change to something with lower potential energy. Okay? So, like we were talking about a second ago, kinetics has nothing to do with spontaneity. What does kinetics determine about a reaction? When we're measuring the kinetics of a reaction, we're typically using a stopwatch or something like that. So what does kinetics say about a reaction? Yeah, that's just the speed, or how fast or slow a reaction. Okay. Influenced by things like activation energy, like we were talking about. Presence of a catalyst, concentrations. Okay. So kinetics, we're talking about some kind of process that will happen eventually. All we're doing is saying, is it going to happen right away, or is it going to take years or months or millions of years to happen? Okay. So that's kinetics. Spontaneity is a completely separate discussion. That's whether products or reactants are favored. Are favored energetically. And what was the chapter that we talked about? What did we call it when we were talking about whether we're favoring products or favoring reactants? If we got a reaction that could go both ways? Yeah, equilibrium. Equilibrium is a consequence of spontaneity. Okay? So kinetics and equilibrium, totally separate things. Okay? Kinetics is just telling us how fast it takes for us to reach a particular equilibrium. Okay? A catalyst or something like that will never change the ratio of reactants to products when the reaction finally finishes. Okay? It just lets us get there faster. Okay? But equilibrium, energetics, that determines whether or not are we favoring reactants or are we favoring products when the reaction finishes on its own. Okay? I think we mentioned this on the last page. If a process is non-spontaneous, is there any way to get it to be, any way to get it to go? Yeah. What did I say we have to do? Yeah. Requires a constant just would require a constant supply okay. Heat can sometimes be used to do that, and it depends on whether the reaction is endothermic or exothermic. But if you have a certain equilibrium constant, you can totally shift that by adding heat. Okay? Heat would shift the reaction away from the direction that you would say plus heat. Okay? If it were an exothermic reaction, you'd have plus heat over on the right. So if you added heat, the reaction would shift to the left. Okay? So while spontaneously it may be going far over to the right, a constant supply of heat would be able to change that. But if we took that heat away, it would go back to the equilibrium that it was at before. Okay? So that's one example. Doesn't just have to be heat, though. There are other ways that can happen. Could be light, could be electricity. Talk about that in the next chapter. So, predicting spontaneity. Remember, enthalpy, delta H, is a measure of how much heat is transferred in a reaction. Okay? Specifically, heat transfer when it is open to the air. That's at constant pressure. Okay? And signs of any of these things are in terms of the system itself. So in terms of system. So if through a process delta H is negative, that means from the point of view of the system, the enthalpy decreased, which means the system did what with heat? Did it give? Yeah, it gave heat away. That decreased the enthalpy of the system because it gave heat away. Okay? So, what did we call that? Exothermic, because the system loses enthalpy by a heat transfer out to the surroundings. Okay? Enthalpy is the term is based on the energy of the system itself that is influenced by heat transferring. Heat is a transfer of energy. Enthalpy is a property of the substance itself. Okay? So, delta H greater than 0, what's that called? Endo. Okay. System gains enthalpy by heat transfer into the system. Okay? So, take a look at water. What's this one called? What's that process called? Freezing. H2O liquid becomes H2O solid. That's freezing. Okay? Delta H is negative 6.02 kilojoules. It's negative because the water molecules had to slow down in order to settle into their little crystal atoms. Okay? The opposite process has the opposite sign. Okay? That's how that works. Melting is endothermic because those solid molecules need to gain energy to speed up to move around. Okay? But the thing is, either can be spontaneous, depending on depending on the temperature. And we could sort of figure that out using a plus heat in the equilibrium or something like that. But the fact of the matter is that just heat in, heat out is not enough to figure out whether something is spontaneous, it turns out. Okay? So just what we want to write down here, enthalpy is not a predictor of spontaneity. There are spontaneous processes that are endothermic. There are spontaneous processes that are exothermic. Okay? So when scientists were first starting to understand energetics, this was a hypothesis that only spontaneous processes were exothermic, but the discovery of some very important endothermic spontaneous processes made a problem with that. If you've ever used a chemical ice pack, okay, you break it up, it spontaneously becomes cold. Okay? When something feels cold, it's sucking energy into it from your hand and from the surroundings. Okay? So that's a spontaneous endothermic reaction. There are lots of spontaneous exothermic reactions, but we're going to need more to figure out what actually makes a process spontaneous. Okay? So